Hello. So it's a great pleasure to be in a room where I can speak about, I can hear the concept ONNX or slides about ONNX without to have one or two slides explaining what it is. So I feel like in a kindred place. All right, so the talk is ONNX MLIR compiler exploiting OpenMP parallelism. Alex Eichenberger and his joint work with various different researchers, both from Yorktown Heights as well as Tokyo. So here's one slide about the ONNX MLIR compiler. So it's a compiler for deep neural networks in ONNX format, so at the present time only for inference. So we start with an ONNX model, and then we feed it to ONNX MLIR compiler. And you're probably familiar with MLIR, so it can lower in various different dialects one at a time. So we have four well-defined outputs. One is a LLVM, so which is very close to what the LLVM compiler will ingest. And then we use LLVM compilers to generate binary. And right now we have CIs that check for x86, ARM, IBM Z, and Power. And there's also three other dialects that are used as an interface to other MLIR compiler. One of it is ONNX, which is almost a one-to-one mapping of the ONNX protobuf to the ONNX MLIR dialect inside ONNX MLIR. And then TOSA, which is kind of a matrix-based dialect, as well as stable HLO, which is used, I believe, in TensorFlow. We have some support for accelerators as well. So we use it for our IBM accelerator on Z. And there's a generic interface that could be used for others to use as well. And this entire thing is open source. And today's talk, I'm going to speak about the path that we actually use, which is ONNX MLIR to LLVM down to IBM Z using AI accelerator. So the machine that we're actually targeting is a highly parallel processor. So we have a system of up to 32 chips. Each chip has 8 processors that are pretty fast. We also have and those are in blue. And then on the same chip, we also have an AI integrated accelerator with more than 6 teraflops of 16-bit precision. And all those share the same L3. So which means that it's really good for low latency communication between the CPUs and the accelerator. And as you can see, there's a lot of parallelism. So and the topic of the talk is try to use this parallelism in order to accelerate an inference. So what we do is first of all, we detect the available parallelism in an ONNX graph. And we do that both in functional level, so like in green, where basically there's nodes that can be executed in parallel, as well as data parallelism within an operation that can be accelerated. We also map then those operations to devices, which is either the CPUs or the accelerator, on-chip accelerator. And we're going to exploit the parallelism a little bit different depending on where we go. And we are lucky in the sense that MLIR has a really good support for OpenMP via an OpenMP dialect. So we didn't have to do much in terms of the low-level mechanics, which is really why MLIR is a good system, we believe. And it provides parallelism for loops as well as sections. And it has really a good affinity, support for affinity, which is useful for us because we have both chips as well as processors, and we want to exploit a different level of parallelism, a different part of the graph in different ways. So the next 3 slides, I'm going to tell you a little bit about how we exploit parallelism for those 3 different situations. The first one is the AI accelerator. So it's really on our machine. That's where things run the fastest. And so we exploit it at 2 different levels of granularity. At one level, we partition across different chips. And so when we do that, we get the benefit of having multiple accelerators. So we have basically the work partitioned along multiple accelerators. And we have increased bandwidth because each one have their own dedicated L3 and pipe to memory. And we also partition work within a chip. And that's what we found is we have a higher throughput when we have several processors hit the same accelerator. And also they have shared memory bandwidth, shared locality in the cache. And so that's also beneficial. So without going too much into the detail, I'll just show you a little experiment. We matrix multiply, so we can tile the A matrix along rows and the B matrix along columns, which is good because we don't have to split the reduction. Then this is how we exploit it on our system. So along the A matrix, we're going to split the tiles among different chips. And then the B matrix, we're going to share it among different processor within that chip. And here is some results. So we can see that And that's for a constant, basically, number of tiles on the A side. And we vary the number of threads, if you want to, within the chip, hitting the same accelerator. And we see that at roughly 8 threads or 8 processors per tile, basically, we get the highest performance. And the speed of is about 12 when we started with 8 accelerators. So it's a little bit of superlinear speed up because we have basically cache locality and we also get some benefit from extra memory bandwidth. So the second part is like we cannot map everything on the accelerator. So sometimes we have parts that remain on the CPU. So when we have an operator that is fully parallel, so we do things that compiler knows how to do. So basically we take a n-nested loop nest and we collapse into a single dimension. And then we parallelize that and we also generate CMD code. And so that behave very well. And then for partially parallel or hard to collapse, then we tend to parallelize the outermost loop using OpenMP. And on a small network like Roberta, so of course what we do is first we place operation on the accelerator, but with Amdahl's law, so once you accelerate those parts, then the remaining work is a slow part, and that's about 70% after we move things to the accelerator. And so when we have batch size parallelism, that means, things that are known to be independent on the outermost loop. So we get roughly a 2x speed up. And when there's no batch size parallelism, then we have to work a little harder to get parallelism within operations that remain on the CPU, and we get to 1.3 speed up. And that's for the entire network, including all the work in the accelerator. So then we also do some functional parallelism. That's a little bit newer. So basically we find a set of independent operations and we typically treat that as outer level parallelism that we move across different chips. And then inside the operation that are mapped to a given chips, we look at exploiting further data parallelism, and there we use multiple processors within the chip. And again, so some experiment based on Roberta. And so the blue is exploiting only data parallelism. That means no functional parallelism. And the orange is this hybrid mode where we both get the data and functional parallelism. And what we can see is that low thread count, it's kind of better to go to as basically not using functional parallelism, doing straight data parallelism. But once you're above a certain threshold, you get better performance. And those are speed ups with respect to sequential. You get better performance by going to functional parallelism first and then using data parallelism within a node. Okay, so in summary, so ONNX MLIR now supports parallel operations. So we extract the parallelism by looking at the graph. We efficiently exploit it in CPU operators, on the CPU as well as on the accelerator. And we do this hybrid functional and data parallelism. So all this is based on OpenMP dialect available with an MLIR, which has a good support also for affinity, which is useful for us. So everything is available today in the open source ONNX MLIR. And the CPU parallelism is really generic for all LLVM targets. So if you had something like this, you can exploit. You could exploit it. We focus, obviously, as IBMers, we focus on our machines, but it's really, we test it and all the CIs work in all the different platforms. And for the accelerator parallelism, so it's a bit more specific, obviously, to the current accelerator that we have. However, the infrastructure that we develop allows you to add also your own accelerator. So we have the hardwire anything, especially for IBM in the generic sense. Thank you.